So, good morning. Today is the week. Today is the week 10 of the Variability session for the course, an introduction to thermodynamics, variability, and monitoring. Last class we were discussing about the atmospheric heating by different species present in the atmosphere, like how they varies, sharp wave heating, long wave heating, etc. We also discussed like how much radiation actually reaches the surface of the Earth in case of incoming short-wave solar radiation, and also how much radiation is being emitted, or how much radiation is being emitted from the surface, from the surface of the Earth, and from the top of the atmosphere as it passes through the atmosphere. These different things we were discussing in the last class. So today we will mostly go through the heating profile of the atmosphere. Suppose some amount of radiation is reaching the atmosphere, how much heating this radiation is causing within the atmosphere. So that's what we'll be discussing mostly today. So I thought we'll start with an numerical. The question it is given that the net upward long wave radiation at a certain frequency is given by the function f of z is equal to 2z square minus 15z. Is it an amount will be equal? I'm not able to write them in the slide. Give me a second. Mhm. Mhm. F of z is basically given as f of z is equal to z square minus 15z plus 150 watt per meter square. So this is the radiation that is reaching the atmosphere. We need to find this particular intensity of radiation is resulting in how much heating in the atmosphere. So that's what we need to find out. So we know that the atmosphere absorbs radiation by which it heats up. It also emits radiation by which it cools down. So this heating and cooling basically determines the temperature profile of the atmosphere with respect to the altitude. So in order to estimate the atmospheric heating, we need to estimate the heating due to absorption of solar radiation and the heating and cooling due to the absorption and emission of thermal long-wave radiation. So in the short-wave range of the spectrum, generally the absorption takes place, but the atmosphere doesn't re-emit radiation back in that particular wavelength. So in the short-wave radiation, the absorption of short-wave radiation generally results in warming. The short-wave radiation generally results in warming, whereas the long-wave radiation, as it gets absorbed, as well as the atmosphere also, after absorbing, it also re-emits it back. It leads to both heating and cooling. So if we want to estimate the atmospheric heating, we need to understand how much absorption is actually taking, how much heating is taking place due to the absorption of solar radiation, and how much heating and cooling is actually taking place due to the absorption and emission of thermal long-wave radiation. So let's consider a horizontal consider a horizontal slab of atmosphere of area A and thickness delta Z at a height Z from the surface. Suppose this is the surface at a height Z. We are considering a horizontal slab of atmosphere which is having a thickness of delta Z and an area A. Suppose the net upward radiation entering entering the slab from bottom is given by Fz of Z. So this means intensity of radiation is entering the slab from the bottom. The A F Z of Z. So this means radiation is entering the slab from the bottom, and the net upward radiation leaving on the top of the slab is given by area into Fz of Z plus Z. If Fz is the intensity of radiation that is going out. So A Fz into Z plus delta Z. This is the radiation that is leaving the slab. So the change in radiation within the slab is given by A into radiation that is leaving, which is Fz of Z plus delta Z minus Fz of delta Z. Fz of Z delta Z. Minus Fz of Z, which gives you A into Fz into delta Z minus A minus A Fz delta Z. The difference and Fz minus Fz, let it be d Fz by minus A delta Z. Let the difference between incoming the radiation that is entering and the radiation that is leaving is given by dFz by dz. So it will be minus A dFz by dz into delta Z. Plus dFz by dz. So the difference in the radiation that is entering and leaving, that difference is basically causing the radiative heating of that particular slab. The difference is basically leading to a radiative heating. So as we know, the difference is given by A delta Z into d Fz by dz is the radiative heating of delta E. Now if we find it per unit volume, radiative heating per unit volume is given by delta E by the volume, which is A delta Z. It will be dFz by dz minus dFz by dz is the radiative heating per unit volume. Now, if you want to find the heating rate per unit mass, it becomes Q radiation of Z which is equal to minus 1 by rho of z into dfz by dz. This is in watt per meter cube, where fz is given in watts. This is in watt per kilogram. Minus 1 by rho z dfz by dz. Anyway, the differential of the intensity of radiation with respect to that is entering the slab gives you the heating rate per unit mass or unit volume. So this F of Z is basically F outgoing minus F incoming. So here in the question, basically, we go back. In the question, F of Z is given, and we need to find the volumetric heating rate for this radiation and for value for this radiation of this frequency 5 kilometers from sea level. In the question, F of Z is equal to 2z square minus 15z plus 150 watt per meter cube is given. So we need to find the volumetric heating rate value for this radiation at a height of 5 kilometers from sea level. So at Z is equal to 5 kilometers. We need to find the heating rate, which is Q radiation. This is given by minus dF by dZ is equal to minus d by dZ of 2z square minus 15z plus 150. So if you find the differential, it will become 4z minus 15 minus of 4z minus 15 or 4 into 5 minus 15. This will be minus 5 watt per meter cube into first. This is like per second. Second inverse can be written as first. So 5 minus 5 watt per meter cube hertz is the answer. So this is the heating volumetric heating rate in this case, and this is the intensity of radiation that is entering the slab, the net radiation. Now, the next question is, so if as I said, this F offset is basically the difference between F outgoing minus F incoming. So if we are considering solar heating, in case of solar heating, only F incoming is there, F outgoing is 0, since after absorbing the radiation, it doesn't re-emit it back in the shortwave. And that when the absorption is happening in the shortwave radiation of the spectrum, the re-emission is not actually taking place. So because of that, only F incoming is there. So if we are considering solar radiation, then this F set becomes F outgoing, sorry, F incoming. In case of solar heating, F set is just F incoming. F outgoing is 0. And whereas in case of long wave radiation, it is the net, like F incoming minus F out. Both are there, both comes into picture. So it is a bit more complicated in case of long wave radiation, whereas in case of incoming solar radiation, it is F incoming only. The next question is state true or false. The shortwave heating rate reaches a peak at the optical depth of 1. So as I said, if we look at the heating rate with respect to the shortwave radiation, so in case of the shortwave radiation, the only we have to consider F incoming. F incoming can be written as F incoming, which is incoming solar radiation at the top of the atmosphere, into e raised to minus tau. So tau is the optical depth. So if we want to find the heating rate Q, it is given by minus 1 by rho Pf by Tz, which will be F is equal to F incoming, which is equal to F incoming from the top of the atmosphere in degrees to minus 2, where rho is the optical depth. So the heating rate is basically given by minus 1 by rho df by dz, which is minus 1 by rho of z d by dz of f into e raised to minus rho of z. If you find the differential, it will become minus 1 by rho of z into f incoming into rho I a new absorption of I into exponential of minus rho of z. Here this rho I can be substituted as rho 0 e raised to minus z by h. Rho of z can be substituted as rho 0 e raised to minus z by h. And then if we find the derivative, like if we simplify it further, we will basically get the equation for the heating rate. So Q rating is basically given as minus 1 by rho of z into F, the incoming solar radiation at the top of the atmosphere, into rho, rho nu a new absorption I in the expansion of minus 2 of z. So here in this question, it is given that the shortwave heating rate reaches a peak of the optical depth of 1. So the heating rate or the shortwave heating rate, when does that reaches its peak? So if we want to find the peak of the shortwave heating rate, you just have to equate this to dq by dq by d tau is equal to 0, which will give you a value of tau is equal to 1. And further, if you look at this in this figure, here the solid line shows the atmospheric heating rate. And the dashed line gives you negative of upward radiance, and the dotted line gives you the exponential decrease in partial density. So the atmospheric component basically decrease with rho is equal to rho 0 e raised to minus z by h. This also we can substitute in this equation, so it will further simplify. So here we can clearly see that, so this the solid line gives you the atmospheric heating rate, and the maximum heating rate is actually occurring corresponding to an optical depth of 1. So the statement that the shortwave heating rate reaches a peak at an optical depth of 1 is true. Now the next question. What is the impact of carbon dioxide on the temperature profile at both the troposphere and stratosphere according to the radiative transfer model. So there are different species in the atmosphere which interact with the incoming solar and outgoing long wave radiation. So we have discussed this before. Each molecule has a specific wavelength upon which it absorbs the radiation that is interacting with it. So if we look at the atmospheric profile or heating profile of different um, atmospheric constituents, each molecule will have its own atmospheric profile. Like at what height it is leading to the largest forming, and at what height it is basically leading to cooling. So here the question is, how does the atmospheric carbon dioxide modify or impact the temperature profile at both the troposphere and stratosphere? So here in the figure, you can see the x-axis shows the temperature and y-axis shows the height, how the temperature is changing for how the absorption is changing for different species. So the blue line basically shows for water vapor, the red line shows for water vapor plus carbon dioxide, and the black line shows for ozone. So we can see the water vapor is basically leading to um, a cooling in the troposphere. So we look at around 10 kilometer. It has decreased from 300 to 200. Around 100 Kelvin decrease we are able to see for a distance of 10 kilometer, or there is a decline of 10 Kelvin per kilometer, we can say approximately in case of water. Now, the question is how carbon dioxide is impacted. Here we don't have a picture of carbon dioxide profile separately, but we have a combined one of water vapor plus carbon dioxide. So it is clear that in the troposphere, both um, yeah. So both the lines of water vapor and water vapor plus carbon dioxide are parallel to each other. So both are actually contributing to a decrease of temperature by 10 Kelvin per kilometer. 10 Kelvin decrease is actually seen in the troposphere. That is decrease in temperature by about 10 Kelvin. So this one is correct. Yeah. In case of yeah, approximately 10 to 20 Kelvin decrease is there for temperature in the troposphere. Now, what is happening in the stratosphere? Now, in the stratosphere, after 11 kilometer, we can see that this blue line is a profile for water vapor. And when it is becoming water vapor plus carbon dioxide, the rate of decrease or the slope of the water vapor line is actually decreasing, which means the rate of decrease of temperature with respect to height is decreasing. Which means when combinedly water vapor and carbon dioxide is leading to a more warmer temperature profile than that of water vapor alone, which means if we are when the carbon dioxide is present, it is leading to a little bit of warming in the atmosphere compared to that of when only water vapor is present, which basically means that it is leading to a decrease in temperature in the troposphere, whereas it is leading to an increase of about 10 Kelvin in the stratosphere. We can see in the troposphere both lines are parallel, water vapor and carbon dioxide lines are parallel, whereas when it became in the stratosphere, as we can see, this difference is actually happening. The moment carbon dioxide comes, so when carbon dioxide comes in, it is pulling it to a warmer temperature, thus leading to an increase in temperature by about 10 Kelvin in the stratosphere. So the answer is the carbon dioxide is actually leading to a decrease in temperature by about 20 Kelvin in the troposphere and increase it by about 10 Kelvin in the stratosphere. So yeah, that is the answer. Now the next question. Why is the temperature lapse rate found to be unconditionally unstable in radiative equilibrium based temperature profile? Uh, So we know like different lapse rate, like environmental lapse rate, adiabatic lapse rate, adiabatic lapse rate, etc. And we have discussed different stability and instability conditions. So unconditionally unstable in the sense it makes the atmosphere always unstable, which means ELR is always less than, yeah, environmental lapse rate is always greater than adiabatic lapse rate and saturated adiabatic lapse rate. So it is always environmental lapse rate is very high. That's what it basically shows. So if we only consider the radiative equilibrium, which means so if we assume that the atmospheres, so till now we were only discussing radiative heating, like from through radiation how much it is actually affected. So only if we are only considering the atmosphere's radiative heating, that is absorption and emission of radiation, and we are getting a very high value of lapse rate, or we are getting a very deep lapse rate. So apart from this radiative process that are happening in the atmosphere, there are other things like convection, latent heat transfer, etc., which actually helps in with a proper mixing the dense atmosphere. So because of that, due to the neglect of convection and latent heat transfers, we are actually having a conditionally unstable atmosphere. So if you look at the temperature profile, so the purple line is basically showing the lapse rate for radiative equilibrium. The lapse rate is very high. The temperature decline is very fast. Whereas the actual value or the global average is the green line, which is around 6.5 Kelvin per kilometer. So that is basically lower than the radiative equilibrium line. So because we are neglecting the vertical convection and latent heat transfers, we are getting this very high value of radiative. This is the due, next option was due to the neglect of shortwave heating process. With radiative equilibrium model, we are considering the shortwave heating due to the rapid turning of the temperature profile because of the presence of greenhouse gas. Because of the negative convection and latent heat transfers, so only we are getting a unconditional or very high value of a steep lapse rate for the temperature profile. Now, using the ground temperature equation, that says Tg is equal to Te into 1 plus tau g by 2, the whole raised to 0.25. Calculate the ground temperature Tg for a scenario where the effective emission temperature is 255 Kelvin and our equivalent optical depth is 4. So if you this basically gives you how to calculate the ground temperature from the emission temperature if you know the optical depth. And the question, we need to find Tg, and the effective or the emission temperature is given as 255 Kelvin, and the equivalent optical depth is given as tau is equal to 4. From the equation we can write Tg is equal to 255 into 1 plus 4 by 2, the whole raised to 0.25, which will be 255 into 1 plus 2, the whole raised to 0.25. This will basically give you a value 335.59 Kelvin, which is equal to approximately 336 Kelvin. So the answer is 336 Kelvin. of the following gases contribute most to long wave cooling in the troposphere? So, if you look at the net heating rate, net shortwave heating and net long wave heating, you can see that the net shortwave heating is positive. That is the Q radiation, Q shortwave, volumetric heating due to shortwave is positive, whereas the volumetric heating due to long wave is generally negative. So, generally, long wave emission or absorption is leading to the net long wave effect is actually a cooling, whereas the net short wave effect is a warming. In the question, we need to find which of the following gases contribute most to long wave cooling in the troposphere. So the figure basically gives you, with respect to height, how the heating and cooling profiles of different atmospheric components like the water vapor, carbon dioxide, and the ozone varies. And it also shows a net profile, like the solid black line shows the net profile, net putting all together, and the dotted dashed lines shows the individual heating and cooling profiles of different compounds. So we need to find which is contributing to long wave cooling, most of long wave cooling. And this is the cooling profile in the troposphere. Troposphere in the sense within 10 kilometer only you have to see. So if you look at the cooling profile, this dotted line is causing, or it is mostly driving the profile in the troposphere, and this dotted line corresponds to water vapor. So water vapor is leading to the most long wave cooling in the troposphere. Now, next question. The vertical temperature profile of the atmosphere under the radiative equilibrium model will lack which feature if ozone is not considered? If we are not considering ozone when we are determining the vertical profile of the atmosphere, which feature will not be there? So here if you can see, this is the heating in case of water vapor, this is in case of carbon dioxide. This is separately for short wave and long wave. Here we have combined and then we are giving the so this black line is for water vapor, carbon dioxide, and ozone combined. So as you can see, water vapor, the profiles of water vapor and water vapor plus carbon dioxide is actually leading to a cooling in the stratosphere also. But when ozone is also combined, that is when it is actually leading to this positive or inversion in the stratosphere. So ozone is the reason for this inversion here, or the turning of the temperature profile in the stratosphere. So if ozone is not there, then the turning of the temperature profile above the stratosphere um, will not be there. It will be like the linear decrease of the temperature profile in the troposphere. So that is contributed mostly by water vapor and carbon dioxide. Ozone is not playing any role in modulating that particular profile. It's almost equal to the water vapor plus carbon dioxide profile and the unconditionally unstable nature of the temperature. So we already discussed. The unconditionally unstable nature of the temperature profile is due to in the model we are not considering the vertical motion and the latent heat fluxes. That's why we are getting an unconditionally unstable. We are only considering the radiative equilibrium. The third one was matching the temperature of the atmosphere at the ground. So that is also a different problem. So the turning of the temperature profile above the stratosphere is what will be missing if we doesn't consider ozone while plotting the vertical temperature profile of the atmosphere. The next question. The high radiative lapse rate makes the atmosphere unstable and causes the development of large-scale convective currents that transport additional heat from the lower to the upper troposphere and thus lowering the temperature level. Yeah, this is correct. So because of the large radiative equilibrium that we saw, high radiative lapse, the radiative equilibrium is actually leading to a large value of lapse rate. So it actually promotes the vertical convective forces or vertical convective currents. So as the warmer air from the surface is rising and reaching the top of the reaching at a particular height, heat transfer is actually happening along the atmosphere, which actually modulates the actual lapse rate. So we have vertical convective currents are actually transporting additional heat from the lower to the upper atmosphere. Question: which factors do not contribute to the net upward long-wave radiation? First one, okay, whatever the Earth is basically emitting, so that is the upward long-wave radiation. So, which of these factors doesn't actually contribute to the net upward long-wave radiation? The spectral transmitter means how smoothly the radiation is actually being transmitted. So that matters um, how much longer radiation is actually coming out of the atmosphere. So spectral transmittance does contribute, and spectral black body radiation intensity. It totally depends upon the intensity of the radiation that is being emitted. Then atmospheric temperature. Based on the temperature only, this emission is happening. It determines like how much intensity of radiation is actually being emitted from each layers. So the answer will be all three are actually contributing to the net upward long wave radiation. So this is the answer. State true or false. Under radiative equilibrium model, the ground temperature and air temperature just above the ground are the same. Statement is Tg is equal to T at Z is equal to 0. This is a statement. They're asking if it is true or false. So the the temperature profile in height is given by Tg is equal to 2 epsilon Tz. Tz is equal to T epsilon, which is the emission temperature, into 0.5 into 1 plus optical depth into exponential of minus z by h the whole raised to 0.25. So when z is equal to 0, it becomes T epsilon into 1 plus 2g star divided by 2 e raised to minus z by h becomes 1. The whole raised to 0.25. So yeah, at z is equal to 0, Tg equal to 3 epsilon into 1 plus 2g star by 2 the whole raised to 0.3z. Now this is Tz at this is the temperature at z is equal to 0. Now what will be the temperature of the ground? The net black body radiation emitted at the surface is equal to upward radiation flux density. So the net black body radiation emitted by the surface is given by sigma Tg raised to 4. And the upward radiation flux density is F outgoing to Tg back to optical depth. This F outgoing and the optical depth is given by half F0 into 2 plus optical depth into e raised to minus z by h. When z is equal to 0, this becomes half f0 into 2 plus rho g. Now, if you keep both, you will get sigma tg raised to 4 is equal to half f0 into 2 plus rho g star. Which implies tg raised to 4 is equal to, from this we can write this f0 is basically sigma te raised to 4. And here we can write f0 is equal to sigma t raised to 4. So you can write sigma tg raised to 4 is equal to half into sigma t epsilon raised to 4 into 2 plus theoretical depth. So finally, tg becomes te into 1 plus 2g star by 2 the whole raised to 1 by 4. Whereas t at z is equal to 0 was te into 1 plus 2g star by 2 the whole raised to 1 by 4. So tg is not equal to t at z is equal to 0. Or tg is greater than t at z is equal to 0. So this is basically a thermal discontinuity. But like z is equal to 0 is very close to the ground. So it should not be like, it should not have a different temperature logically. But in our radiative equilibrium model, the issue is like the discontinuity is actually happening since we are not considering the convective heat transfer from the ground to atmospheric layers. So because of that, it is actually different. So here, under the radiative equilibrium model, the ground temperature and air temperature just above the ground are same. It's a false state. Okay. So I guess these things like how the radiation is getting transferred within the atmosphere and what is the heating profiles of the atmosphere. These things are clear, I guess. And we will go for different topics, such as basically the different forces present in the atmosphere, what is basically driving the wind circulation in the atmosphere. The first question is, which of the following forces does not drive atmospheric wind circulation? The main forces that drive the atmospheric wind circulation include the Coriolis force, the pressure gradient force, the frictional force, and the gravitational force. So the force that does not drive atmospheric wind circulation is the magnetic force. So the answer is magnetic force. So what is the angular speed of the Earth's rotation? We know that the Earth is not at rest. It is actually rotating in its own axis from west to east. So the value of the angular speed of the Earth's rotation, which is generally given a notation of omega, is 7.29 into 10 raised to minus 5 radians per second. This is the next question. An originally north-moving wind will get tilted to the northwestern direction. Similarly, we can show that a south-moving wind will get tilted to the southeastern direction. So, as we said earlier, there are different forces that basically drives the wind circulation in the atmosphere, like the Coriolis force, the pressure gradient force, frictional force, and the gravitational force. So, the pressure gradient force actually drives the movement of the wind. The wind generally moves from high pressure to low pressure areas. The um, frictional force generally slows down or creates a hindrance to the flow of motion. Gravitational force generally determine the movement of air in the vertical direction. Now, what does this Coriolis force do? How does Coriolis force affect the um, movement of air in the atmosphere? So, what is basically this Coriolis force? So, Coriolis force is an apparent or pseudo force which arises due to the rotational motion of the Earth. Since the Earth is actually so suppose we have Earth, suppose there is an air parcel in the atmosphere, and assume that there is an observer. Uh, there is an observer which is watching the air parcel from the surface of the Earth. So both the observer and the air parcel are moving um, as the Earth is rotating. Since both are on the surface of the Earth, we know that the parcel is at rest. Now consider that the observer is actually watching from another frame of reference, which is not moving along with the Earth. So then, when that observer will see, it feels like even though the air parcel is in rest, due to the rotation of the Earth, it feels like the air parcel is moving. So this Coriolis force comes into play when the observer is or with respect to the non-inertial frame of the rotating Earth. Because of the rotation of the Earth, this basically um, acts. So what are the reasons for the the Coriolis force basically has two components. First one is due to the conservation of angular momentum. The second one is due to the centrifugal force, which is acting due to the rotation, but it will be in direction towards the center of the Earth. So due to the conservation of angular momentum, when a body is moving um, uh, with respect to the non-inertial frame of reference of the Earth, and the centrifugal force which comes into play due to this rotational motion of the Earth. Because of these two reasons, the Earth actually, an apparent or pseudo force actually acts on the Earth, which is basically known as the Coriolis force. Now, if we what is the equation for the Coriolis force? The Coriolis force is basically given by 2 omega p sine phi into I minus q sine phi into g. So this is the equation for the Coriolis force. So what does it mean? Like if suppose a body is moving, it has so you suppose if we represent the wind in vector form, ui plus wj plus omega k. This is the wind velocity. U plus its zonal component, zonal velocity, which basically gives you the velocity in the west-east direction. And V is the meridional component, which gives you the velocity in the south to north direction. And W is the vertical component, which gives you like along the atmosphere, upward or downward. So generally, if you consider wind or any motion in the atmosphere, it has three different components. So V basically gives you the motion along the south-north direction. U basically gives you the motion around the west-east direction. So this, what does it basically mean? What does the Coriolis force basically means is that if suppose a body is moving in the south-north direction, the Coriolis force will start acting in the I direction or west-east direction. It will become like this. Um, if it is moving in the positive V direction, suppose if it is moving in the negative V direction, uh, south to north, sorry, north to south it is moving, then the Coriolis force will act like in the negative I direction or east to west. So here, coming back to the question, it basically says that an originally not moving wind in the northern hemisphere, not moving in the sense that is moving like this, it will get tilted to the northwestern direction. Exactly due to, but when the wind starts moving, it has a meridional component of wind. As it starts moving, because of the Coriolis force, it will get tilted to the northwest direction. So this is the northbound moving wind, and this is the northwest wind. We essentially yeah. So it basically get tilted to the northwestern direction. Similarly, a south moving wind will get tilted to the southeast direction. This is the formula for the Coriolis parameter is given by. So as I said, the Coriolis force is given by 2 omega p sine phi I minus q sine phi j. And here we can take 2 omega sine phi as common. 2 omega sine phi into ei minus uj. So this particular component 2 omega sine phi is known as a Coriolis parameter. F is 2 omega sine phi. This is the Coriolis parameter. Then the pressure gradient force always moves air from high pressure to low pressure. So yeah, pressure gradient force basically leads to the movement of air from high pressure to low pressure region. I will give you the equation for the pressure gradient force. The pressure gradient force by M basically minus 1 by rho is P by dou H from the I minus 1 by rho So P by rho y, j direction, minus 1 by rho dou P by dou z and P by. This can be rewritten as minus 1 by rho dou P by dou z is basically G. So the K component can be replaced by G in the hydrostatic equation. Or if you want to write the pressure gradient force in terms of geopotential, remember geopotential is given by minus G dz. The dz is basically dP by rho. You can write G delta z is equal to delta phi equal to delta P by rho. Or you can write the pressure gradient force along the x direction as minus 2 pi by dou x. The pressure gradient force along the y direction and direction as minus 2 pi by dou y. So if you plot the geopotential from sea level to the higher altitude, if the geopotentials are having the geopotential surfaces are having a steeper slope, it means like large pressure gradient force exists there. So from the slopes of the geopotential lines, we can actually determine what is the strength of the pressure gradient force over that region. So as we move along the geopotential height along the x direction, if we are having very high slope, then it means large pressure gradient force is present. And when we are moving in the y direction along the geopotential, if there is steeper slope, again it means there is a large pressure gradient force in y direction. So that's how we generally determine or we find the pressure gradient force along different direction. So yeah, so here the question was just to asking the pressure gradient force always moves the height from high pressure to low pressure. So yeah, that was correct. Now, at which latitude is the Coriolis force zero? So we know F Coriolis is given by 2 omega sine phi into Pi minus Qj. So phi is basically the latitude. Sine phi is equal to 0. It means F Coriolis is equal to 0. Sine phi should be 0. What will be the value of phi? Phi will be 0 degree, right? And sine 90 is 1. Sine 0. Sine 0 is 0. Yeah. But 0 degree, at 0 degree latitude, the Coriolis force will be 0. 0 degree is the okay. And that was the last question. We'll end of the class here for today. We will continue the discussion on the next class. Thank you.